Okay, how much of the topic can you guys remember? Kinetics, not much, right? Okay, so we're gonna do slowly now. Right, okay, so can you guys look at, we are looking at part A, right? Okay, question 2A. They gave us a couple of things and okay, just pretend you have a graph paper lah. Okay, we are just gonna get this part quickly over with. Okay, so for A part 1, you're supposed to plot in graph. Okay, what will be the axis like? Okay, it's what against what? Yeah, okay, what would the axis be like? Well, okay, based on the data they've been given to us, right? Okay, can you guys remember what are the two graphs that we learned in kinetics? Rate concentration, okay, that's one. The other one is concentration time. Okay, just based on the data we've been given, okay, what should we be drawing? Okay, it's a rate concentration graph. Okay, yes, so we have zero order, first order, second order, right? And all we need to do here is to pick the correct axis. So what will be our y-axis here? Which one of the data? Okay, our rate, right? Okay, so we just have to first, okay, just go and draw this out also. Okay, if you guys need some paper, you can just let me just split. Okay, yeah. Okay, just split some of the paper around. Okay, so in other words, okay, we are going to have to draw a rate concentration graph, okay, or rate against partial pressure. They are the same thing, right? Okay, what's the x-axis over here going to be like? Okay, so they gave us two sets of data. Okay, so it's either partial pressure of NO or partial pressure of NO squared. Okay, let's draw both up. Okay, if you plot partial pressure of NO over here, then what will you be getting? Okay, so let me just show you guys the shape now. Okay, because you're supposed to determine the shape yourself with a graph paper. We don't waste time with the plotting here now. Okay, but if you were to plot this graph, right, you'll get something like this. Okay, someone just tell me, right, what can you infer from this shape? Any idea? Okay, rate against partial pressure of NO, you get a curved graph. Okay, so is it zero order, first order, or second order? First order, really? Okay, so the thing is, right, if rate is against partial pressure of NO and you get a straight line, then what order would it have been? Yes, it would be first order. But now that there is a curve, right, can we conclude there's a second order graph? Is it conclusive enough? Okay, because if you realize something, right, it could be third order, it could be fourth order, it will all be exponential curves, right? The higher the order, the faster the rate gets over time, right? Okay, it gets faster and faster. So this is not conclusive enough, guys. Okay, take note. A conclusive graph, right, must be what shape? Is it a curve? No, right? It should be a straight line passing through the origin. Okay, because if it's passing through the origin, we can conclude they have a what relationship? Directly proportional relationship. Yes, okay, so in other words, guys, this is not conclusive enough if you end up plotting this graph. Okay, so let's just pretend, okay, what is the second graph that we're going to draw to get something more conclusive? Concentrate, okay, but we don't have time. That's the problem with this question. We don't have time, right? Okay, is there another set of data I can use? Okay, look at the data they've been given. Okay, NO squared. Okay, they have actually given us, right, okay, the partial pressure of NO, but then they square the value. Okay, so let's just plot that onto our graph as well. So N square N minus 4. Okay, let's just follow the units. Okay, and let's just skip to the important part, right? When you actually plot this graph, right, I will actually get this as my shape. And what can we infer from this graph over here? Okay, it is conclusively a second order graph. Okay, so that's what we need to plot from now on. Okay, take note over here at the side. Okay, whenever there's any rate concentration graphs, okay, it is only conclusive if you obtain a straight line passing through the origin. So if you see a curve, it could mean second order, third order, fourth, fifth. We have no idea. Okay, so we need to confirm by checking whether square is a straight line or not. Okay, so yeah, okay, that's our first idea here. Okay, so with that said, right, okay, I want you guys to go and write down the answer, go and phrase your answer for part 2, okay, because they asked us to use our graph, okay, to answer part 2. Okay, so give yourself like maybe 2 minutes, okay, go and phrase the answer over there. Okay, and if you were to do this in exam, right, okay, do you think you have time to draw both graphs? Definitely not. Okay, you only have time for one. And guys, next time when you see there's a square data, right, there's a reason why they gave you that, right? Okay, if there's a reason why they gave you the square data, then you just draw that immediately. You can see this first. You can game the system a little bit, okay, by drawing the square data, you can just ignore the non-squared data, basically. Okay? Right, so just get the words out for part 2. Okay, so describe the shape a little bit, then you give me a conclusion. Like what can you determine from the shape and all that, right? Okay, if you're done, you can just read part B also lah. Okay, you can give part B a try also. Okay, so let's quickly go over our part 2. Okay, so what will you need to include in your answer? Okay, how do you justify the order of reaction? Okay, so first of all, describe the shape. So you can just tell me, right, okay, when red is plotted against PNO squared. Okay, so you specify which graph you have drawn. Okay, you can just say a straight line graph passing through the origin was obtained. Okay, the passing through the origin part is very important. Okay, because that signifies a directly proportional relationship. Okay, without passing through the origin, okay, then you cannot conclude anything from that. So this part over here, just go and highlight in your answer also. Okay, you might want to highlight, underline, whatever. Okay, passing through the origin. Okay, and then from here, what can we infer? What's the relationship that we can infer over here? Rate is directly proportional to what? The square of NO. Yes, okay, good. So you can just say rate is directly proportional. If you don't want to spell everything out, just use this simple over here, right? It's proportional to partial pressure of NO square, which then signifies what order of reaction is this? Second order. Okay, so then you can tell me reaction is second order with respect to NO. Okay, and take note, right? Okay, I use WRT lah for short. Okay, honestly, you don't need to spell everything out. I think that's a bit waste time also. Okay, but no questions in this, right? Okay, we talk about shapes. Okay, then afterwards, I need you guys to look at part B. Okay, for part B, let me just give you guys like 3 minutes. Okay, then I will talk about this question. Right? Let me highlight the important parts for part 2. Okay, got 1.5 minutes left. We'll talk about it. You want to discuss whatever, go ahead, right? Okay, later we'll still discuss. Oh my god, the first thing I do, I thought that was AU again. No, I didn't know. Oh my god, you look like AU. I was scared for a moment. Oh, but that's a scam. Because acai is more expensive. Then if you get the salty, right, it's cheaper. Yeah, you think about it. It really looks like. Hey, don't have the negative thoughts. No negative thoughts. You say, but that's why you fail, right? No, no such thing. This one? On paper, okay, we can set one lesson for that, since I've seen you guys 6 times in November, right? Yeah, I mean, okay, yeah, that's normal, that's normal. Like, you don't want to face your fears, right? Like, you don't want to see that again, right? No, you have no choice. You have to look at it again. That's the only way to get better. Okay, can we go through this question? Okay, so what can we determine? What can we determine from this question here? Okay, they said, right, okay, the same graph was drawn, but the gradient was half. Okay, so what could that mean? The partial pressure of oxygen is half, and then the gradient end up halving also. Okay, so what's the first instinct? What order of reaction is this? 0 first or second? Second, it should be first order, okay? Because if you halve the concentration and then the rate is also half, it is directly proportional, right? Okay, but how do we justify our answer here? Let me show you guys a more conclusive way of looking at it. Okay, I want you guys to let a rate equation of this question, okay, be partial pressure of NO. Okay, NO is squared. We determined that already. Okay, but then, okay, you know what? Let me just place my oxygen first. Okay, you'll see this more clearly. Partial pressure of oxygen, then partial pressure of NO squared. Now we do not know what's the partial pressure of oxygen, like the order. So we're just gonna put an X. Okay, we leave it there first. Okay with this? Yeah, okay. And I want you guys to take a look, right? This graph over here, the y-axis is rate, the x-axis is NO squared, right? So what does that mean now? A straight line, what's the straight line equation? Y equals to mx plus c, right? Okay, there's no c here, right? Okay, so it's just y equals to mx. And I want you guys to take a look here, right? Y is your rate, x is your partial pressure of NO squared. So can someone tell me what is your m? Okay, basically this entire chunk over here, right? Okay, so this is your m, and m represents the gradient. Okay, so in other words, I want you guys to go and write down your gradient of this graph, right? Is basically just k and partial pressure of O2 to the power of some order. Okay, we do not know what that order is. So let's confirm a few things. Okay, so when you halve the concentration of O2, does the rate constant change? No, it's not rate constant, right? Rate constant is only affected by what? Temperature and activation energy. Yes, okay, good. So in other words, okay, guys, I want you all to take a look. This question, they halved the partial pressure of O2, right? And what happened to the gradient? What did they say? Okay, it's also half. Okay, what does that infer, right? Okay, this is power x, right? So what does x actually represent here? Just 1 law. Okay, so that's like a more mathematical way of looking at it. So that's what we can conclude. X equals to 1. Okay, let's write a bit of words inside, right? But that's basically our answer already. Okay, so you can just tell me the grade. Okay, you write these two statements out first. Then you can just give me a final statement. Okay, when partial pressure of O2 is half, okay, the gradient is also half. Okay, so that implies, right, okay, half to the power of x is just half, it's the same thing. So x is equals to 1. Okay, so you can leave it like that. Okay, reaction is first order with respect to oxygen. Okay, so that's a more technical way of looking at it. Okay, so if you look at gradient, right, in general, you should come out with a y equals to mx plus c equation. And you see how this affects, okay, directly. Okay, so the gradient is the partial pressure of oxygen. Okay. Alright, I don't think C is difficult. Okay, so go and do C and then go and try D as well. Alright, D is the one where you have to play around with the equation. Okay, but C should be quite simple. Okay. Alright, for C and D, I'm gonna give you guys like 5 minutes to try. Okay, most of the time should be spent on part D, not C, right? What's homogeneous catalyst? Homo means what? Same what? Same state as the reactants. So let's say your reactants are equals, your catalyst also equals. So it's homogeneous. What's the opposite of homogeneous? Hetero, meaning what? Different states. So if you have gaseous reactants, use a solid catalyst, different one. Yeah, okay, so that's another one. Now everything is a gas. So that's why it's homogeneous. Okay, think about the property of a catalyst. What must a catalyst do? What does it usually exhibit? Right? Especially when you have two steps. When you use a catalyst at the start, what happens at the end? Okay, ask yourself questions. Right?
Wrong.
Okay, maybe I give you guys a bit of clue, right, for part D. Okay, but perhaps let's look at part D first. Okay, for part C, okay, rate equation, I don't think this is that difficult, right? Okay. Your rate constant. Oops. Okay, so your rate constant over here has to follow the units that are given in the question. Okay, so again, right, when you solve for rate constant, I want you guys to always pretend it's a math question and just place rate constant as the subject of this equation. All right. So once you've done that, right, okay, you must tell me first what the units for rate. Okay, that's usually the case, right? But you need to follow the question. So over here, the rate is m minus 2 and per second. Okay, we just follow suit. All right, okay, and then what's the units at the bottom over here? Okay, so there's basically m minus 2, but then there's 3 of it, right? So you just cube the whole thing. Okay, it's like mole per diem cube, then you cube the whole thing also because there are 3 terms over there. Okay, you can see that. Okay, so you have 1, okay, then what's the resultant? Power 1. Here is power 1, here's power 3, so then becomes, okay, power minus 2, right? So n minus 2, then m is what? 4. Yes, okay, take note, -2 times -2 gives you 4, and then it's just per second. Okay, so that's a unit for your rate constant. All good? So treat it like a math question. It's literally math, right? Okay, but I want to talk about part D. Okay, part D, they are asking you guys to kind of come up with something with the steps. Okay, not say very easy also, but it requires a little bit of clue. Okay, I need you guys to understand the catalyst portion first. Okay, any issues with part C before I move on? Okay, Okay, coming to part D again, you just need to highlight the words homogeneous catalyst, right? Okay, what does a catalyst do? In let's say this reaction here to oxidize SO2 to SO3, it can be done in like one simple step, right? Because oxidize means you add what? Oxygen, right? Okay, it can be done in like one step. Okay, but if it's done in 2 steps, what property does it show about a catalyst? Okay, what's the definition of a catalyst? Okay, it increases the rate of a reaction by lowering the activation energy, but there's something in between, right? By providing an alternative reaction pathway. It sounds very cheap, right? But all that means is that this reaction can be done in 1 step, but then now it is now 2 steps because it's just an alternative way of doing the reaction. Okay, and another thing is catalyst, right? There's one very important property we discussed last time. A catalyst must be what? Regenerated at the end of the reaction. Yes, okay, so it's regenerated at the end, right? Meaning to say, at the end of step 2, what must you have? There must be an NO2 there. Okay, you're going to use NO2 at the start, and then NO2 must appear at the end of step 2. So we just have to bear that in mind. Okay, and then of course, now we just try the question. We just try step 1. Okay, so next time when you see this kind of mechanism questions, okay, first SO2 must react with, SO2 is the starting compound, right? Okay, so you must start off with step 1, must react with what? Okay, must have NO2 inside, yes, okay. And then let's just put our arrow. Okay, what are we going to get over here? Okay, of course, there are plenty of possibilities. Okay, but you just need to make the guess. Okay, what are some possible answers that you all have? Okay, just mention. SO4. Okay, if you got S, okay, we entertain as many possibilities as possible. Okay, I'll talk about SO4 first, then I'll come back to carbon later. Okay, so SO4 and okay, the thing is, SO4 is usually what? SO4, then 2 minus. Yes, okay, so this doesn't exist. Okay, there has to be a charge there, but then how come suddenly got carbons? No, right? Okay, what was the other answer just now? Okay, before we come to that, okay, that's correct. Okay, but sulfur is what? It's just S. Okay, yeah. Then what's next? What else do you do? Okay, O2 and NO. Okay, so this is also another possible, okay, but it's not balanced, right? Yeah. Okay, let's just say we balance it out. Okay, so again, there's nothing that disproves this, right? Okay, it looks fine so far. I mean, as long as you balance it, it seems fine. Okay, but then the thing is, right, the issue is always the second step. Again, the second step at the end of the day, right? Okay, just now we mentioned that SO2, okay, should oxidize to SO3. Usually this is done in 1 step. Then what's in between? You must add oxygen, right? Okay, because that's just oxidation. Okay, so you should only get these things in the overall balance equation. Okay, but then the thing is, right, I have sulfur over here, which makes it kind of difficult, right? Okay, so there's actually an easier way of doing this now. Okay, so I want to get SO3, right? Can I obtain SO3 already from the first step? I can, right? Okay, I can get SO3 first. Okay, then what should be my other guy, other product? Okay, it's just NO, right? Because I just shift 1 oxygen from here to here. Okay, so I get NO. Okay, so far, what are we missing? Okay, refer to the overall equation. What are we missing? Okay, we don't have oxygen yet. Okay, so sure. Remember at the end of the day, what must we get? You must get an NO2. Okay, so we put one NO2 at the end first. Okay, oxygen must appear on the left side, right hand side. The left, okay, because O2 is on the left, right? Okay, so we just add the half O2 first on the left. Okay, then what's the remaining thing that you need to add also? Okay, in order to get NO2. NO. Okay, so that basically completes the puzzle, right? So notice a few things. You must first understand that the catalyst is regenerated, so you can put this at the end first. Okay, it must be there. And then the thing is, right, I already got SO3, so settle already. I use SO2 on the left, also settle. And you notice, right, guys, this NO has to cancel each other out because one on the left, one on the right. It doesn't appear in the overall equation. And of course, oxidation means you need oxygen also based on the overall equation. So sometimes it's better, right, to look at the overall equation first and then just play around with the different possibilities. Yeah, okay. So again, this one not say very easy also, because you're supposed to guess. Okay, and with more practice, you'll be able to guess this a bit faster. Okay? Okay, anyways, okay, go ahead and try your part E. This one also quite fast. Okay, then afterwards, you can move on to part F also. Okay, come, we just do E and F. Okay, give you guys about 5 to 6 minutes. Okay, E and F, not difficult, right? Okay, 1 mark, so don't need to explain too much. If phase and state is the same thing. Oh. Yeah. Phase is just the more, state is something that we normally use like when we talk about state symbols, right? Okay, but phase and state is same thing. Okay, we can look at the Boltzmann diagram. Try to remember how to draw Boltzmann, right? If we no choice, need to remember, right? Oh, they don't. Fortunately. Is it very cool? I think I see things in the aircon going directly. I think most of you guys forgot about the graph, maybe, right? Except for Chauffeur. Looks like you really right. But that's correct, that's good. You're supposed to memorize it. Yes. Yes, the mountain, yeah. The hill. Okay, I think this warrants a revision time. Okay, I'm gonna just go through this with you guys again. Okay, and then just take note of how to make this a bit easier for you guys. Okay, part E. For part E, what's the answer here? How will you describe heterogeneous? They ask you just describe the meaning of that word. Different. Yes, different states. Okay, so you can just tell me that the catalyst is in a different state from its what? Yes, reactants. Okay, you can either use the word state or phase, is fine. Okay, but yeah, okay, that's pretty much the answer here. Okay, come in with the products, right? Okay, because catalyst is supposed to speed up the reaction between the reactants. Okay, so it's just these two guys. Okay. All good? Okay, then we look at part F. Okay, part F is Boltzmann diagram. Okay, it's just one of those things where you need to memorize. Okay, and eventually when it does come out, okay, it will pay off. Okay, so first of all, the Boltzmann distribution diagram should be this thing here that's passing through the origin. Okay, it's just this little mountain thing, very steep on the left, very gentle on the right. Okay, and then what's the y-axis? Can you remember?
Energy level.
Energy should be on the x-axis. Okay, so this is the proportion of molecules actually. Okay, and then down here, then is the energy. Okay, so take note, right? Can you remember what is the area under the graph? What does it represent? Okay, the number of molecules, yes. Okay, so the proportion is on the y-axis. The area is like your integration like that, right? Is your total amount of molecules. Can see that? When you add the catalyst, do the total amount of molecules change? No, right? It just speeds things up. Okay, in fact, a catalyst is supposed to do what? Lower the activation energy, yes. Okay, so over here on the far right, right, usually that's where your uncatalyzed activation energy is. And then your catalyzed activation energy, just lower it. So you must move it towards the left. And that's pretty much it already. Okay, so you just now have to do the shading or whatnot. I'm a bit lazy to shade, so I'm just going to label A and B. And then you need to come up with a legend as well. Okay, under this legend over here, what are the areas that I need to discuss? What's the first thing? What first area?
Total area.
Okay, total area, you mean the whole thing?
Yeah.
No, it's not. Okay, we are only concerned with the molecules that have energy that is more than the higher than the activation energy. Okay, so before you catalyze the reaction, okay, this area A, right? After you catalyze the reaction, is area 1. A and B, yes, okay, good. So don't just write B because it's everything beyond to the right of the activation energy. So clearly A plus B is bigger, right? Okay. So again, you just need to mention this. A is the number of molecules because it's the area. Okay, we already mentioned area is the number of molecules, okay, with kinetic energy more than or equal to the activation energy. Then just specify that this is the uncatalyzed EA. Repeat the same thing for A plus B, but now is KE more than the EA that's catalyzed. Just a lot of words to write out, okay? But then the graph itself, okay, probably about 2 marks. And then the final mark is to come up with the explanation. Okay? Okay, all good with this? Okay, to answer the next part on okay, how do you explain this, right? Okay, how does it actually increase? Okay, I want you guys to split it into 3 parts. Your answer is 3 parts. The first, you go and write the definition of a catalyst. Define the catalyst. Okay, so we just need to mention, okay, what's the definition? Catalyst. Okay, okay, so a catalyst, you can say increases the rate of the reaction by providing an alternative reaction pathway that has a that has lower EA. Okay, that's the first thing already. Okay, just copy and paste the definition. Okay, the second part, right? Okay, you're gonna tell me about the increase in proportion of molecules. So you're just basically copying down it A again. Okay, so the number of molecules, okay, with kinetic energy more than or equal. Okay, the activation energy, is it the catalyzed or the uncatalyzed version that we are discussing? They're asking about adding a catalyst, right? So it should be the catalyzed version, right? Okay, so we are focusing on this catalyzed version. As you can see, there's a higher number of molecules. Okay, so you just say it increases based on what you can see from the graph. Okay, and then the final step is always the same thing, right? We better for all Boltzmann diagrams, whether it's temperature or catalyst, what's the last step here? How the rate that increases means there is more what? Remember, forwards. Frequency of yes. Okay, so frequency of effective collisions increases, and that's directly tied to rate. So that's why your rate increases. This is a template answer. So it's like when you if you study this, this is the whole thing. You just copy and paste this from your head into the paper. Okay, that's pretty much this person. Okay, so it's really just a chance to get 3 marks. Okay. At the same time, we can discuss part 2. We can just do on the spot. right? Okay, so yeah, okay, let's just discuss the answer for part 2. Okay, again, how does a catalyst affect the rate constant? Okay, it will lower the activation energy, then consequently it will, what does it do to the rate constant? Increase or decrease? Okay, it will. Okay, increase, right? Okay, guys, just take note. Rate constant and rate, right? Okay, they move in the same direction. So if the rate is faster, rate constant will be higher, right? Okay, so it's the same thing. Okay, so the idea is that here, just remember that rate constant is affected by temperature and activation energy, which is basically affected by catalyst. Okay, guys, when you increase temperature, is the reaction faster or slower? Okay, faster, right? Okay, because more effective collisions and whatnot. Okay, so increase in temperature will lead to an increase in rate constant. Okay, guys, in order to, so it's just getting faster, right? Okay, guys, so when you add a catalyst, what happens to EA? EA is lowered, and then the rate constant will just increase also, because it just becomes faster. You can think of it that way. Rate constant, faster means higher, slower means lower lah. Okay, so just tell me that as your answer. Okay, the catalyst will lower EA and hence increase the rate constant.
Sorry, how is lower EA? Oh, because temperature is proportional to.
Yes, okay, but in fact, right, okay, because the rate constant actually has this equation over here, which you don't need to know, okay, but it's basically this, if I'm not wrong. I'm also not very versed in it. Yeah, okay, so the thing is, right, because this is a negative power, right? Okay, so a negative power, if I change it, right, it's just like that. Okay, negative means, what do you call it, denominator, right? Okay, so in other words, when you increase your temperature, okay, when you increase temperature, what happens to the E value at the denominator? Okay, so that's just math really. Okay, just take a look. Okay, if your T increases, that means the fraction here will
be
low. Okay, just a fraction, not the power, as in the EA over RT. It becomes smaller. Okay, so the E to the power of something smaller will give you a smaller value, right? Okay, so a smaller value over here, that means K will be higher law. Okay, but you don't need to know this equation. This is the rate constant equation that is not tested. Okay, so you actually scrap this lah. Okay, but that's how it works. Yeah, okay. Just know from now on that faster means K is higher. Yeah, okay. Lower activation energy means K is higher. Faster mark. Okay. Now, let's complete G and H. G and H is a little bit more on chem bonding, right? Yeah, go ahead. That's it.
Sorry. Okay, oh. That means what?
Yeah, it is metal. It is platinum is metal, of course. It doesn't matter lah. The word transition there don't know that. PT.
Like the diagram. Do you want us to draw this one with that?
Yeah, correct.
5-4.
Try. Yeah. Then remember what is a metallic structure made out of? Yeah, what was a metallic structure? Yeah, okay, all that. Just draw whatever you think you can draw. Okay, the more important part is to explain lah. Okay, so just explain why metals have high melting point in general. Yeah. Okay, just focus on that. Sorry. Okay, here you don't need to write the symbol. Yeah. Don't need to write the platinum symbol. It's fine. Okay, the charge here, okay, because you all are not really thought of platinum, right? Okay, so the charge, you put any charge you want now, honestly. Just put plus. Yeah, just put plus carry. The cation just put plus. Okay, because I don't expect you guys to know what's the platinum charge lah. Okay, this one even H2, you are not thought of that. Draw like 4K already. You don't need to draw so many. Why you draw like 28? Don't need so many. Don't need so many. If not, you end up wasting your own time also. Just draw like 4K already, man. Like 4, 5 settle. Okay, part H, just read the question. Okay, then just think about it. Because we'll discuss part H together. Okay, but for part G, this one you're expected to know lah. Okay, I can also. Hang on, yeah, poisoning in context of a heterogeneous catalyst. No, just think about it. Okay, now what we'll do together. Right, we'll discuss together. Okay, think of a few reasons first. Okay, but I just highlight go and highlight the keywords that are on the board here. Okay, you could think of poisoning in this context here, right? Okay, they have narrowed it down to the fact that it's only poisoned by things with lone pairs of electrons. And you must think of it as a catalyst, not just a normal metal. It's a catalyst, right? Okay, come on, whatever theories you have. Okay, we will discuss this question. Okay, but in the meantime, just make sure your G is done. Okay, can we go through G first? Okay, this one is just a metal, right? Okay, metal, what does the structure of a metal contain? Okay, giant metallic, okay, what's actually inside the thing? Okay, cations of the metal and C of delocalized valence electrons. Okay, so again, that's what I'm gonna explain in our answer. Okay, but again, I don't expect you guys to know platinum is what charge. Okay, even if you look at the periodic table, it's like in the middle of nowhere. Okay, so it's just okay, let's just pretend it's a plus charge. Okay, let me just draw like 4, right? Can already. Okay, honestly, 4 or 5 looks nice, can already like that. Okay, then just surround by electrons, okay, in between. Okay, something like that. Finish already. Okay, because actually it's good to write the platinum metal, but again, I don't expect you guys to know platinum is what charge. Okay, if platinum can exist in a lot of different charges. That's why I don't expect you guys to know, right? Then just put a plus charge there. Yeah. Okay, can? Okay, then the next thing is to explain why does it have a high melting point? It's because it has very what? Very strong what? Okay, electrostatic forces of attractions, blah blah blah. Okay, then you need to specify also, right? Okay, so platinum has strong. Okay, if you don't want to write electrostatic forces, remember you can just replace it with what? Electrostatic, blah blah blah, very long, right? So you can just tell me strong metallic bonds. Yes, okay, so I prefer you guys use this. It has strong metallic bonds between between the cations and okay, yes, okay, don't forget the word valence. Okay, someone said valence. Okay, yes, only the valence electrons in the metal can delocalize. This is a misconception. Okay, okay, C or D localized valence electrons. Okay, and then finally, how do you link back to melting point? Yes, again, energy. So which requires large amounts of energy to overcome. Yes, okay. No, you're repeating yourself, right? Can electrostatic forces, okay. Okay, but the main idea is that I usually like to, to avoid repeating yourself, right? Okay, just go and like say comma which requires large amounts of energy to overcome. Settle already. I think that's a lot better, right? A lot more optimal. No lah. Is it doesn't matter? Doesn't matter. Can. Must have the plus. Okay, because it's metal cation ions and C of localized valence electrons. Cation ions, okay, so it cannot be the atoms, it's not the atoms. Okay, this one quite important. Okay, so can we look at part H? Okay, this is a rather interesting question. Okay, but you guys must, okay, this kind of questions will always come out in exam one. Like questions where you need to think. Okay, remember some of the context here, okay? Here, guys, it is prone to poisoning. Okay, of course, it's not the literal poisoning. Okay, they put in what's that thing called apostrophes here. Okay, so it's poisoned by ions or molecules with lone pair. Highlight the lone pair of electrons. That's the main driving factor of this question already. Okay, lone pairs of electrons. Okay, and this nickel here is in the context of a catalyst. Okay, so first of all, it's a heterogeneous catalyst, right? So it's just a solid piece of metal over here. So just imagine this. Okay, it's just a solid piece of metal here. This is your nickel. Okay, can you remember how does it work? How do heterogeneous catalysts work? Okay, it's a different state. Okay, good. That's why it's a metal, right? Okay, and then imagine this. Okay, there is okay, imagine there's gaseous reactants. What do the gaseous react? How do they interact? It starts with a letter A. Right? Adsorption. Yes. Okay, no attacking here. Okay. So yes, the gaseous molecules, can I just pretend it's like, I don't know, like carbon monoxide, nitrogen monoxide, something like that. Okay, because a lot of the times, right, okay, when this happens, right, they will undergo adsorption, so they must do this thing here. It's like so-called they're being attached to the what?
To the surface of
What's the surface? What are the active sites? Yes, okay, guys. The gaseous reactants must be absorbed onto the active sites of the nickel. Now, these active sites, right? Okay, are they like infinite? No, right? Okay, the active sites, okay, once it's occupied, okay, then you have less active sites. Agree? Okay, now the thing is, right, come back to the idea of poisoning. When this thing is poisoned, that means can it still act as a catalyst? Can it still attract and attach all these gases? No lah, cannot. That's why it's called poison. Why can't it attach? Why can't it no longer absorb? Now it's being occupied by who? Whoever with lone pair of electrons. Can see that. So in other words, let me just repeat myself. A catalyst, in order to work, it needs to have free active sites to absorb the reactants, right? Attach here, attach here, attach. Okay, but then there's limited active sites. So if you're gonna have unwanted people, right, with the lone pair of electrons forming bonds with the nickel, right, that's gonna occupy some active sites, right? And then can you still undergo normal absorption? No, you can't. So it's just hindering its catalytic activity. That's the idea behind this question. Okay, and the thing is, okay, now that you all understand how this works, okay, why did they say lone pair of electrons? The lone pair of electrons will form what with the nickel? Lone pair. You give the lone pair, what kind of bonding is this? They bonding, or just you can also mention covalent bonding. Yes. Okay, the lone pair of electrons can be given now. And then okay, let's deep our answer even more. Okay, how come nickel, right, can accept lone pair of electrons from like nowhere, from like other molecules? It can expand its octet. Okay, good. That's the answer here. Okay, if it can expand its octet, right, that's why it can accept lone pair of electrons from other people, right? Okay, and we can't just say it expands octet. What's the phrase we need to say? Nickel has energetically accessible vacant, good, 3D orbitals. Okay, so if it has these orbitals, right, it can accept all these lone pairs from the other unwanted, like ions or molecules. Okay, so you can tell me this, it can accept the lone pair, so I bring in the lone pair of electrons from the unwanted ions or molecules. This is basically the poisoning part happening already. Then the second half of this question is to now tell me, right? Okay, yes, okay, you accept lone pairs. Now, so what? How does it link to it being a useless catalyst now? Why is it that it forms lone pairs, it forms bonds, then it becomes useless? Why? No more active sites. Yeah, okay, like what we discussed. Okay, so now you can tell me, okay, does the active sites will become occupied? And if it's occupied means what can it not do now? It cannot, what's this process again?
Absorb.
Okay, it cannot absorb the whatever reactant molecules. Okay. Okay, so and reactant molecules cannot be absorbed. Okay, can no longer be absorbed. So let me just highlight all the keywords in this question. Okay, remember absorb is spelled with a T. Okay. So I first talk about how it can expand this octet. If it can expand octet, that means it can accept the lone pairs of electrons from all the other unwanted molecules. Once it accepts already, there's less space, there's less active sites. Active sites become occupied. When it's occupied right now, right, it's just a worse catalyst, just a shittier catalyst, right? Okay, because it can no longer be absorbed. Very, very good question. Go ahead and start this. Okay, they really made this as very as vague as possible, right? Okay, but then they give you guys some clues here and there to consider. All right. Yeah, okay, exam style question. Okay, we are here to try challenging questions. The easier questions, I'll just leave you guys to do at home, right? You realize it's easier. Yeah, okay. All good so far? Right, we'll do a little bit more of the next question, not the whole thing. Okay, we do a little bit more of the next question, question 3, and then we take a break afterwards. Okay, now we just do a little bit more. Okay, so if there are no more questions, I want, okay, let's try a shorter question, question 3. We're gonna talk more about your kinetics and all. Yes, we are like halfway through. It starts to not become kinetic right here. Okay, so come, can you guys turn over to question 3, right? Just try part A first. Okay, just A. Okay, a lot of times exam questions is not just one topic, right? Okay, it's not constrained to one topic. In multiple topics can appear in the same question. Okay, so that's why, yeah, go ahead. Okay, so go and try part A of question 3. Okay, balancing of equations. Okay, remember how do you balance oxidation or reduction of equations? Okay, see you. Bye-bye. Yeah, supposed to balance the elements slowly. Yes, correct. Okay, to balance oxygen, go and add water. Okay. Then how do you balance the H? You add the H plus. Yeah. Okay, try that first. Okay, balance OH. Balance oxygen with water. Balance H with H plus. No electrons. Fine. As in you need to balance with electrons, definitely. Yeah, but then now the charges are not balanced, right? Oh, because the H plus not balanced properly. The left side you have 11 H plus, the right side you got how many? That's not balanced. Confirm with electrons. Actually, both are fine. Yeah, both are fine. But it's always electrons last. Yes. Okay, sure. Or like, he's your junior or you retain? Oh, retain. Okay. So, can. Now probably have to see him soon also. You can maybe send me his number. After class. Okay, come. Let's go through this question. Okay, for 1 mark. Yes. Okay, can right. You have to balance all the elements first. Okay, so carbon is balanced, hydrogen later you balance, oxygen later you balance also. Okay, that's why they told you guys, right? Nitrogen is a product. Okay, so you can just add N2 gas over here. Okay, so N2 is it balanced now? Are the nitrogens balanced? Yes. Okay, so what's the next thing to balance? The first thing to always balance, right, is your oxygen. Okay, oxygen first. So I have 4 on the right, 2 on the left. So what do I do? 4 on the right, 2 on the left. So I add 2 water. Okay, so you add 2 more water, then now the oxygens are balanced. But in the process of adding water, I also the H plus, the H is now not balanced, right? Here I have 12 here, sorry, 11 here. So here must also have 11, right? So how many H plus must I have? Here, 6 H plus. Okay, but unfortunately, they did say one more thing. Basic conditions, good. Okay, so basic conditions, what do we need to do? How many? Yeah, okay, you want to neutralize all the H plus ions, you add 6 OH minus on the right and on the left. Okay, when you add things out of nowhere, you need to add on both sides. Okay, that's because you want to balance. Okay, now can we just tidy up this thing? What should we do? Okay. H plus OH minus gives you 6 water. So 6 water on the right, 2 water on the left. End up with 4 water on the right hand side. Okay, so you just erase this. Go and write there 4 water. Erase the water on the left also. Then let me just bring the 6 OH minus up. Okay, so now all my elements are balanced in the basic conditions. What's the last thing to do? Okay, electrons. Okay, what's my charge? Okay, how do I add the electrons here? On the right. Okay, oxidation is losing electrons. You must have it on the right. Okay, so no matter what, all the rules are always the same one. You can't remember, I'm going to write down the rules. Okay, always balance, again, aside from all the weird elements, right? You must always balance oxygen with water first, then you balance H with H plus. Okay, but then the next thing is you must check whether acidic or basic conditions. If it's basic conditions, I just put a star here, right? There's an additional third step, which is balance your H plus with OH minus. And the OH minus, remember, must be on both sides. Finally, then you balance your charges at the end. If this was an acidic condition, right, then you can just jump straight to the last step. Don't specify, you assume to be acidic, yes. Okay, basic, they confirm will specify. All right. Okay, I want you guys to just take some time to read the next part of the question, right? And then we're gonna help you guys out a little bit with this, okay? Because usually I teach this thing in practical, okay? But never mind. Okay, just gonna read through this question. It looks complicated, but it's just random reactants, okay? So okay, go and try that. Okay, read the next part, and then you can just read part one. Right, then I'll give you guys the formula to calculate your part one. Right. Okay, so read through the question already. Okay, part one, part two, part three, right, are like questions you normally see in the practical paper, like percentage uncertainty, or uncertainty of the instrument, all that. Okay, never mind. Okay, we don't care about all the three that we don't care about all these three parts yet. Okay, I want to just break down this question. Okay, you all read that paragraph, right? Okay, this is known as a clock reaction, literally because you are just timing the thing, right? Then calculate you are just finding the time taken using your stopwatch. How does this reaction work? Okay, so this is a unique reaction, okay, under this thing called chemiluminescence, where you see color, you see light, those bioluminescent things, right? Okay, so they're saying this, if you read the question carefully, they said that when the two solutions are mixed together, this reaction begins. Agree first? Okay, so they say, right, after this guy UA is completely oxidized, then the second reaction will begin. Can you see it's sequential? First reaction happens, blah, 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 then end ready, then the second one starts. What happens the moment the second reaction starts? See color, right? Okay, you see some like light color. You can see that? Okay, then the moment you see the light, what do? Imagine yourself doing the experiment. You stop the stopwatch. Okay, so that's one experiment done already. Can see that? Okay, guys, so the time taken is T, right? Okay, they say that. So in other words, guys, the second reaction, right, only begins after the first. So can you all think about it, right? The time taken, right, is actually the time taken for what to happen. The other one, what was the other one? One or two? Yeah, okay, just refer to one. Okay. The time taken is the time taken before the light appears, right? Okay, but there's another meaning to it. The reaction 2 only happens when reaction 1 finishes. So technically the time taken T, right, is for the time taken for 1 to finish. You can see that. Okay, this idea is like quite a common idea in the clock reaction. 2 only happens after 1 finishes. So technically you're just waiting for 1 to finish. So time taken T is the time taken for reaction 1 to finish. Because the moment it finishes, then you see some light appear, which is reaction 2. Right? Okay, so just take note of that, okay? And then now let's take a look at percentage uncertainty. Alright, okay, we calculate this together because I haven't taught you guys percentage uncertainty yet. But in other words, percentage uncertainty, okay, physics students might know a little bit of this. Okay, it's just the total uncertainty, right? Over the reading. Okay, so what's uncertainty? Basically, every instrument that you use in the lab, right, for some sort of margin of error. Okay, nothing's ever accurate, right? Okay, so there's this error. They told you guys what's the error here for measuring cylinder. Okay, 0.2 lah. So that's the margin of error there, right? Okay, so to give you guys a better idea, right? Okay, what's error? Some of you guys can't really see. Okay, everyone has used a ruler before. Imagine this is 1 cm cube, or 1 cm, this 2 cm, right? How many divisions are there in between? Okay, that's 10 divisions, right? Okay, guys, you have okay, pretend it's 10 divisions. Sometimes, right, when you all measure something, right, it just nice falls here. They all seem to just nice falls within the smallest divisions. Okay, that's why, right, uncertainty is also known as half the smallest division. Okay, so in other words, here it just so happens that for a measuring cylinder is 0.2 lah. Okay, so the thing is, how many measurements did we take here? Okay, we measured 2 times. Okay, there's FA1 and FA2. Okay, so can we just find the total uncertainty first? What's the total uncertainty? Times 2. Okay, so it's actually 0.2 and 0.2 add together because, guys, can you all see I'm using the measuring cylinder twice? The more you use instrument, will there be more error or less error? More error, there's a higher chance of making mistakes if you use the thing more, right? Yeah, okay, so that's our numerator, guys. What's the reading here? Okay, let's take a look. No, 10 is the size of the thing. Okay, but reading is in how much you actually measure. Okay, so it's 2.5 plus 2. Yes, okay, so that's how you do this thing long. Okay, so I will talk about this next year when we talk about practical more lah. Okay, percentage uncertainty, this formula will be used in some practical questions. But I'm just going to cover this here very quickly lah. Okay, so you're just going to find this in percentage. Okay, you go times 100, you get this as your answer. Okay, again, these are not questions that are really too concerned with. Okay, so just to move on, we discuss this together. All right. Okay, come, read part 2. Okay, and just tell me what are some ways, right, we can reduce percentage uncertainty? Yes, it has come out from Chem in practical, right? Oh, okay, that's viable here. Okay, but pipette cannot, can a pipette measure like 2.5 cm cube? Pipette measure how big? The one you use in the lab. It's like 25, right? It's like, can you measure 24? No, right? Pipette is like a standard calibrated amount. So pipette is no choice lah. Okay, it's like 25, 25, 25. The smaller one is just 10. There's no 2.5 pipette. Okay, is there something very, very precise instrument that you always use in the lab? No, please. Okay, how do you, the most accurate way to measure volume? No, chopper is not. Burette, yes, exactly, guys. Use a burette because how do you justify it in this question? To reduce percentage uncertainty, okay, use a burette instead. Okay, the word precise, okay, let's not throw around these words because that was more physics really. Okay, in terms of this question, a burette has lower what? Yeah, basically uncertainty, correct. Okay, so use a burette as it has smaller uncertainty. You don't even need the word percentage inside. Okay, basically it's a more precise instrument. Now I don't want you guys to throw around the word precise because there's difference between precise and accurate. They are not synonyms. Even ISO is a physics thing. People ask me about that. Yeah, okay, but guys, I want you guys to write down another thing. Can you guys look at the formula here? I want to reduce percentage uncertainty. What can I do? I reduce the total uncertainty by doing what? What did I just do? I reduce the uncertainty by using a more precise instrument, right? Okay, that's how that's one way, right? What's another way in case they ask you about 2 ways? I can reduce the total uncertainty or yes, exactly. I can increase the reading. So guys, what's the reading currently? Is it big or small? The thing is ridiculously small. And guys, that's why in the lab, have you ever done 2.5 cm cube, 2 cm cube mixed together, then just a little bit of puddle just like reacting? No, right? Right, okay? We put at least 25 cm cube, 50 cm cube, because the larger the reading, the smaller the percentage error. That's the idea. Okay, just math here, right? Okay, so go and write this down. Okay, use or just measure and use larger volumes of FA1 and FA2. Answer. Okay, so this one is just something you need to take note. Just take note of typical stuff, right? Okay, so next time you can remember this. Okay, again, part 3 is just a follow-up to that. Okay, guys, what's another source of error in this kind of measuring time experiments? Good. Yeah, that's one answer. Okay, yeah. It is. Okay. Okay, slaying. Okay, so there's this thing called human error, but if you guys human error, it is not enough because guys, humans are stupid, right? We can make so many errors. We can make so many mistakes, like maybe like instrument you don't never wash properly, right? So human error, you must specify what time.
Reaction time.
Okay, reaction time. So human error, okay, could arise in the form of reaction time. Right? Everything to do with human error will be this question lah. Okay, so other sources of error here, right? Anything to do, okay, like guys, when you see the light, or okay, that could be reaction time also. Okay, never mind. Okay, then we can just stop there, right? Okay, any other questions here? Okay, so apart from this, the next few parts are more kinetics based, right? So okay, I want you guys to do C and D first. Okay, then later we can take a break. D part 1, sorry. Right? Okay, so C and D. Yes, right? Okay, yeah, go. Okay, C and D part 1, the focus is on these two. Okay, for part C, just look at experiment 2 and 3. Look at the values in experiments 2 and 3. What are you actually doing between these two experiments, right? Okay, you guys all know how to do D part 1, right? Okay, just slowly go and do. Right. Okay, after we are done with this, we can shoot. Yeah, so usually this question, if your concentration change, then you compare the rate, how it changes also, right? Yeah, okay, but they now give us rate in the table. Okay, so you must remember to do one thing. Yeah, this question here, you just need to take note of one thing. Okay, usually this question here, if the concentration change, okay, first of all, you're supposed to pick out two experiments in which one. Usually what are the two experiments? Okay, well, the others are constant, usually, except for the one guy that is changing, right? Okay, so give me an example over here. What two experiments can I consider first? Okay, 1 and 2. Okay, so 1 and 2 helps us to consider this HRP, right? Okay, so concentration change, and then the next thing you need to investigate is how the rate changes. Okay, but they never give us a rate, what? Then how? Okay, they actually gave us a formula to find rate in this question, right? So in other words, guys, you need to actually find the additional column, add in an additional column where they told you guys that this is rate, so you just calculate this. Okay, so you just have to divide, go and take your concentration of UA, divide by your T for all 4 experiments, and then just jot it down in this column over here. Okay. Okay, then afterwards, when you get a rate, right? Okay, then it's your job to compare experiment 1 and 2, 1 and 3, 2 and 4, whatever. Okay, to go and find the 3 orders. Okay, right? Not difficult, just yes. Because like a lot smaller because you forgot about all these. You just took the face value as times 10 to the power. Okay, guys, don't forget about this thing here. Each one of them is times 10 to the power of 5, minus 5, minus 7, minus 5. Yeah, okay. That's why your value here is different from mine.
What?
Yeah, okay. You must look at the table over here, right? They actually said all these are times 10 to the power of minus 5.
Like this. No, it doesn't matter.
No lah, as in when you find the rate that time. Okay, I know it doesn't matter because you're doing the change, right? Okay, but then as in you want to find the rate that time, these are the actual values lah. It's a lot smaller than it looks. Okay, because the concentration is times 10 to the power minus 5. Yeah, that's true. Okay, yeah. So yes, doesn't matter. Okay, it wouldn't affect your final like order lah. Okay, because it's a change that is same. Yep.
The other two are zero order. Only one is one.
No, that's correct lah.
Oh,
Yeah,
sorry.
good job.
Oh,
That's
okay,
correct
okay.
one, yeah. Yeah, must trust your answer. If not, in the exam then you just start out. No. The chem paper is history. Now we look forward. Wise words.
Wait, just not one for me, right?
I mean, if you want to do part 2 also can lah. Yeah, but just do only part 1 first, lor.
No. Wait, HRP one, then the rest is zero, right? Okay.
Yeah, you can proceed over to part 2. It's like another standard question. Right?
Okay. No, 1 and 2, 2 and 3. Second, is it just seconds? I think so. Okay, I tried physics with me now. It's really okay, just second. Yeah, I think yeah, it should be. No, I trust the physics. I trust. Oh my gosh, Cassie got vice pattern. No.
Okay, so I got the answer for D part 1 here. All good with this. Just have to repeat this 3 times. Okay, I think this method you guys are quite familiar already. All good? Okay, then for D part 2 is just that. Okay, so you have just one guy in the rate equation. Okay, then they ask for units of K. So yeah, okay, so over here you just need to type. Again, if you're not sure, just shift it to the other side. Okay, so what is it? Okay, S per second, yes. And yeah, that's for part 2. Okay, go and try part 3, then we take a break.
Yeah. I'm so sure my I was so sure. I was thinking of this and yeah, same. I'm so sure. Yeah, same. Oh, what's going on? I'm big. Yeah.
The last question, last question. Pass here.
Who is okay, guys, later. This is an interesting.
Yeah, correct.
When you see, is it like this? Consider will review. Consider is a I mean, already enough, right? This doesn't mean already not like. Wait, consider is a Cantonese here. Huh? No, but read. Oh. No, oh, wait, no. Wait, it will decrease, No, but it will be generated. The time is not.
They got a nice sketch of the local.
Wait, is this something you see before?
It's just a concentration time graph. Definitely you've seen this before, right? Your first
Yeah.
concentration time.
Okay.
Okay, suppose you guys drew the same graph with this one, right? Okay, because you see this graph is first order reaction with respect to each other. How does a first order graph look like for a normal? Okay, how does it look like? Concentration time, first order graph. It's just a curve and half-life constant. Okay, but if you draw that, right? Okay, you get 1 out of 2 marks. Because that's what the answer key said. Like, you only get partial credit if you draw a first order graph with constant half-lives. Because the answer to this question is actually just this. Okay, and don't worry about it because you at least get 1 out of 2 marks. I mean, it's fine. They at least give some marks for that. Because from the teacher's comments, they said like basically almost the whole cohort who did this paper drew the first constant half-life. Which is still good, okay, because you guys at least acknowledge, you know how the first order graph looks like. But why is it constant? This is now Gemma also said the answer. This was a catalyst. Yes, okay, they highlighted multiple times in the question that HRP is a catalyst. And I want you guys to take note over here at the side, okay, don't just draw this. Okay, why does a catalyst remain constant throughout? Okay, because it's regenerated. Yes. Okay, so just take note, a catalyst doesn't take part in the actual reaction. Okay, yes, it does provide an alternative pathway, but it doesn't actually take part in the reactants, right? Okay, so its concentration doesn't actually decrease in the reaction. Okay, so just go and mention this. HRP is a catalyst, and take note from now on, right? Okay, its concentration remains constant throughout. Okay, but okay, we talk about this first. Okay, remains constant throughout the reaction. Okay, but if you draw a first order graph, you can still get 1 out of 2 marks. So yeah, you never waste your time. Okay, still can get marks. Okay, just from now on, just know concentration, order of a catalyst. Okay, we thought catalyst concentration always constant. But now take a look, guys. How does that fit with the idea of the question? A first order graph shouldn't look like this one, right? If a catalyst doesn't change, then how does it affect the rate of the reaction? Okay, I hope you all realize, right, that a catalyst should usually actually appear in the rate equation because you think about it, a catalyst is supposed to speed up the reaction, right? So that's why a catalyst needs to affect the rate. You can see that. I repeat, catalyst must increase rate, so it must obviously be inside the rate equation. If it's zero order, that means the catalyst doesn't work. No, it doesn't affect the rate. What kind of catalyst are you using? Right? Okay, so it appears in the rate equation, right? But the graph doesn't correspond to a first order graph. Just take note of that for catalyst. Just slightly tricky, okay, but now we know. Okay. And okay, we take a break first. Okay, later we can continue a little bit more. Okay, we take a break, maybe like 8 minutes. Okay, then we continue. Right. Yeah, okay, I forgot to go through part C just now. It's actually quite a simple question. Okay, guys. Part C, why do you keep HRP and H22 constant for 2 and 3? What's the purpose of keeping other things constant? Is to study what exactly? Okay, guys, remember just now, no, it's all that idea. Okay, you see, right, when you compare two equations, right, you compare like rate 1 and rate 2. Why do you pick 1 and 2? Okay, why did I not pick like 1 and 4? Why is 1 and 2 so convenient now, guys? Okay, because everything else is constant, right? And then how about 2 and 3? Because this question is talking about 2 and 3. Okay, the others are constant except for UA, right? So that's answer to the question already, right? Okay, so for part C, you just need to tell me, right? Okay, by keeping the rest constant, you repeat that. Okay, we can study, okay, how changing the concentration of UA will affect the rate first. Yeah, okay, it will affect the rate of the reaction. Okay, and so that we can then determine the. Okay, so we see how concentration affects rate, and then so we can study the order lah. Okay, yeah. Okay, so we can determine the order of reaction with respect to UA. Yeah. Okay, so this is about UA, right, for 2 and 3, which is what you kind of did in the working as well. Okay, and yeah, let's continue with part E. Okay, they say explain fully. So you need to break down the word homogeneous catalyst here. Okay, go and look, remember the definition of a catalyst. Okay, and you see how that is applied into this reaction pathway, right? Okay, they say explain fully, so don't hold back. Okay, go and go and write down whatever. Okay, make your answer as substantiated as possible. Okay, yeah, that's one. You can. But the key idea is the word regenerated. Yeah, can begin and change is the same thing. Okay, but that's only one aspect of a homogeneous catalyst.
Let's put the time. Other than the video. Like it's created in the image. Okay. So fine, and then one on. Create. You got these
Sleep. Got this.
Oh yeah.
And just explain as much as you can homogeneous catalyst. Okay, just explain that. Okay, there should be about 3 things that you should mention in your answer. Okay, so have we discussed it? Okay.
Yes.
Okay, what's one thing you can tell me? They say explain fully, so we really need to break down the idea of homogeneous catalyst. Okay, homogeneous means again, okay, same state. Okay, that's one thing you need to talk about. Now, catalyst, okay, there's a lot more things to talk about in the catalyst, right? Okay, based on the reaction pathway here, what are some properties of the catalyst that it exhibits? Okay, yes, you see the HRP is regenerated at the end of the reaction. Okay, at the end of the step 3, right, which is the end of the reaction. Okay, there's also another thing you can talk about. Okay, can you all revisit? Go and remember what the definition of a catalyst is. What other properties of that definition, right, is also applied over here. Okay, alternative reaction pathway. Yes, okay, because this reaction probably could have been done in like 1 step, but then now it's split into 3 steps. Okay, now it's okay, to really beef it up more, right? Okay, yes, you have alternative pathway because now you produce what?
You have an intermediate.
You have intermediates. Good. Okay, having intermediates like X and whatever they say, right? Okay, X and Y, that doesn't appear in a normal pathway without the catalyst. The catalyst creates these intermediates. That's how we know there's an alternative pathway. Okay, so that's what you can mention as well. The first two I think is quite obvious. Okay, but then the third one, okay, talk about this also. Okay, so H2O2 and HRP react to produce intermediate X. Okay, and the fact that you are producing an intermediate already goes to show that there's an alternative pathway taken. Yeah, okay, so 3 things. Same state as the reactants, regenerated at the end of step 3. So it linked to this pathway here, right? Okay, for part F, okay, they ask you to outline something. So usually sounds like a very long question, but it's only 1 part. Okay, so we can keep it short. Okay, so let's discuss this. How do we determine if temperature affects rate? Okay, how can we modify this experiment? Yeah, you can just change the temperature, right? Okay, it doesn't have to be increased, you can decrease it also. Okay, so you can just say, okay, change the temperature, but at the same time, you must keep what? What else must you maintain? Okay, you must maintain the concentration of the reactants, right? Okay, because that's not what you're investigating. So you have to make sure that is remaining constant and you only change temperature. So that's the 2 things you need to mention here. You need to mention your control and then the independent variable. Okay, so you can just say, right, okay, keeping the concentrations of FA1 and FA2 constant. And once I keep it constant already, okay, then you can say, okay, repeat the experiment with different temperatures. Okay, and measure rate. That's a dependent variable. Rates. All good with this? Yeah. Okay, we still have a little bit of time left, right? Okay, we kind of started slightly late also. Okay, so can you guys we just go over the question 1, easy question, right? And I just need you guys to do part 1 and part 2. Similar to what we've done just now already. Okay, so once we do this one final time, then we are done for today. Okay. So okay, we have done 2 long questions. Okay, now we try that 1 short question, question 1. Just A part 1, A part 2. With this, you test questions from your school. You guys have just done 2 RI questions. You have to keep that in mind. You guys have just successfully done 2 RI questions. Okay, AC questions should be nothing compared to RI questions. Right?
AC is nothing.
That's not what I said. That's not what I said. I feel like this is a trend. Everyone will hate their own school. I don't know why. But there's so many people on this. I thought like this defining birth rate. Right. Who's the
Yeah. Hey, I remember doing this with my teacher. Yeah, because it's total. Yeah.
You trust your answer, just try it. Okay, part 2 is what we've been doing so far already.
Get it? Yeah. Okay, I'm trying to find any like found out.
One of the orders, right, unfortunately, is a little bit tough, right? Because there are no two experiments in which the carbon monoxide is the same.
Yeah.
Okay, so you just have to do the math as per usual. Yeah, okay, so because you already have determined that carbon monoxide is first order, so you can just put in the values of carbon monoxide inside as well. Okay, so I chose 2 and 3. So 2 and 3 carbon monoxide has changed, and the methanol has also changed. And it doesn't matter because you already determined that the CO is first order, so you can calculate it still. Like, okay, I sub in everything already, right? I can simplify it to this. And then what do I do now? Okay, I just bring this over to the other side, right? Such that my y becomes the subject. Okay, so I will get 0.4y, and then this is equal to what? Once you bring it over. Okay, just take this, divided by your 2/3, is that math? Okay, you can get 0.4 also. It will end up like a nice value, lah. Okay, not to worry on. Okay, because your y has to eventually be an integer value. Okay, which is 1. Okay, that's why your reaction is first order with respect to what's this? Methanol. Okay, both for first order reactions. Okay, right? Yeah, this question here, quite simple. Okay, we have done this plenty of times already. Okay, initial rates method. You compare the initial rates like this. Okay, all good? Right, okay, the other two parts, okay, just go and finish up on your own. And then there's also one final question in this paper, right? Question 4. Okay, I want you guys to go and do this at home. Okay, and then again, yeah, okay, just to make sure you guys do also, right? Okay, go and take a picture and send me as well. Okay, again, yes, question 4. You want me mark the question also can lah. Okay, but it's just one question, question 4. Okay, just do it by next week. Okay, it's just one question, shouldn't be that big of a problem, right? Then just send me a picture on WhatsApp or whatever. Yeah, then I can just quickly mark it or something. Just like how we do our remedial worksheets lah. Okay, by right, this should have been a remedial worksheet, but we went through kinetics separately. You know? Okay, if no questions, yeah, that's it for today.